Otherwise, I have to finish it. So, screen, is this visible to you?
Yes, sir.
Just still there entering. Just a minute. So I think to this point we completed last day. I think this part was over. Now we were discussing this one, voltage control, isn't it? Here, variable voltage, constant frequency. Okay. So,
Sir, audio is not clear.
Yes, sir. Sir, you are not properly audible.
I'm not properly audible.
No, sir.
So shall I change the network? I will try. Still, it is not audible properly.
No, sir, it's okay now.
Is it okay?
Yes, sir.
Okay. So actually, I think we were discussing the speed control techniques. The first one we finished, that is the pole changing method. And the second one, as we derived from the equation, like from here, that the second one will be that whenever we try to change the torque, so it has got a relationship with voltage. So keeping everything constant, let us say all other things constant, so it is approximately proportional to voltage square, right? So by changing the voltage, actually we can change the speed torque characteristics, and then if the load torque characteristics is same, so then when the motor speed torque characteristics is changed, so naturally there will be a different operating point at different operating speed, right? So in this method also you can achieve speed control. So now we will discuss that how the change in voltage can take place when an induction motor is connected. So still a lot of people are entering. So then again I have to switch back and right. So you see that how the voltage change to an induction machine can be effective, right? So first of all, the first thing comes into mind that you can easily have a variac, right? You can have a variac that will have definitely changing the input voltage to the machine, right? But the problem is that this variac principle is not, permissible. It is permissible, but not commercially viable, you can say, because the rating of the variac has to be same as that of the motor, right? So therefore additional cost, and variac is a spacey, you have seen in the laboratory also, it's a spacey equipment. That means it requires a lot of space. So just you will not afford that to have a large space for placing that variac in most of the applications. So therefore variac, that is the first one, transformer, which is rarely used. So control using transformer, that's what it is indicated here. That transformer, or that is actually variac, it is rarely used, right? So second one is actually thyristor voltage controller, phase angle controller. I think you have read in power electronics. What is
Yes,
phase
sir.
angle controller? Phase controller, phase
Yes,
controller,
sir.
right? So now here actually you see the thyristors will be connected anti-parallelly, like this one. This one again one person is entering. Just a minute. So the thyristor will be connected back to back in each phase, and then that phase will be connected to the motor. So this circuit diagram, or you can say circuit diagram, you can say is similar what is shown in the screen. To say, similar to what is shown in the screen. So now you can change the triggering angle of the thyristors so that the effective RMS voltage impressed across the phases are changed. So in this way, actually, you can achieve a variable voltage input to the motor. But one thing you can see that at very larger switching angles, like say above 90 degree or around 90 degree or so, so from 60, 70 and onwards. So apart from the fundamental, introduction of other harmonics also, I mean, gets increased. So the quality of the voltage supplied to the motor is not perfectly sinusoidal. So therefore, it can give rise to you can say some harmonic currents, harmonic torques, harmonic heating effects, etc. So apart from that, this is very effective as because I mean the controller size and the control technique is viable as per commercial points are concerned. So then it is written that voltage control by firing angle control. So now the third point you look at that for operation in quadrant 1 and quadrant 3 only, right? Quadrant 1 and quadrant 3. So what is quadrant 1, quadrant 3 operation that you know? That means quadrant 1 is actually that direction of rotation is forward and it is motoring, right? It is motoring. Quadrant 2 is actually, it is generating, right? Generating operation in the forward direction. Quadrant 3 is again reverse motoring, right? Motoring in the reverse direction. So quadrant 4 is actually generating in the reverse direction, right? So 1 and 3 is possible, and then you can say 1 means actually it's easy forward motoring, but for quadrant 3 you require phase reversal of phase sequence. So you require another contactors or something here before the thyristors, and then you can make arrangement that with the one contactor it is in positive phase sequence, say RYB, and in the other for the other contactor it is a negative phase sequence, that is RBY, and then you can as usual control this triggering angles to achieve different voltages. So now look at the mathematical model for that. So how it can take place. So you can write that that Vs is actually will be in between say 0 to V rated. So by this triggering angle control, you can only reduce it below the rated value, isn't it? Because you cannot increase the voltage above rated value, so that will be affecting your insulation and other parameters. So therefore, no motor is allowed to operate at a voltage which is much higher than the rated voltage. So of course, up to certain tolerance is available. So 10 to 15% higher you can give for some amount of time, but not for a longer period. So therefore, actually, the voltage variation will always take place below the rated voltage, right? So that is why it is written as 0 less than Vs less than equal to Vs rated, right? Vs will vary between 0 to Vs rated. And then from torque equation that we know, torque is proportional to Vs square, that we have already said, that when Vs is reduced, so torque will reduce and speed reduces. Now you see that let us assume that a factor, say B into Vs rated, right? B into Vs rated is applied where B is less than 1. So therefore, the torque equation gets changed to like this: 3 into R dash by S omega S into BVS square by this one. So everything remains same, only that Vs is getting replaced by BVS, right? So then naturally you will have a lower torque which is achieved. Now just a minute, someone has again come. Right. So now you see that we have written few things. Now this type of speed control is actually effective when you have a torque characteristics which is either proportional to the square of the speed, or this is non-linear, you can say, or proportional to Q of the speed, something like that. And naturally, fan and pump drives are having torque characteristics like this. It's proportional to square or cubic of the speed. So now you see these characteristics, right? See these characteristics. Now you see that the top characteristics is for a voltage which is 1 per unit. That is why it is written as B is 1. That is 1 per unit voltage. There is a rated voltage, right? This is the torque speed characteristics. And then this is T by TEM in the y-axis in per unit. So that is why you reach a maximum torque of 1 per unit. So this is, I mean, a reference, you can say, the reference we have considered here. So now whenever the voltage is getting reduced, so the torque is getting reduced by larger amount, as because it is proportional to square of the voltage. So naturally we have a very say decreasing characteristics when we reduce voltage to lower values, say up to 25% or 15% like that. So now let us assume that instead of these characteristics where we have shown load characteristics, where we have shown that load is proportional to omega square, that means it is a fan type of load, let us say, right? Or sometimes it is omega cube, right? Omega square or omega cube. So then you see that with change in voltage, the operating point shifts from, say, first one is A, second one is B, C, D, like that. And you see the operating speeds corresponding to this. So corresponding to the first say characteristics, like at 1 per unit voltage, the speed is something above, say, 0.8 per unit or something, 0.9, say, let us say 0.9 per unit. Maybe we have exaggerated the thing. So normally it operates at rated value at around 0.95 or 0.94 per unit. So let us say it is 0.9 per unit. Now at, say, a 25% voltage, so it reaches a speed of, say, 0.5 per unit, let us say. So there is a 40% reduction, so around 40% reduction of speed. I mean, actually you can achieve little more. So it is just a, I mean, a standard, I mean, just a kind of a display, you can say. This is not for actual exact actual fan characteristic, or you can say operations. But you can have a idea, you can have an idea like that how the speed can fall, right? The speed will definitely fall. But if the load characteristics would have been a constant torque load, let us say it's a constant torque load, it is a, say, the torque is around, say, 0.3, right? Torque is around, say, 0.3 or 0.25, right? So then you see that if the torque is 0.25 per unit and having a constant value, so naturally at lower voltages it will not work, because the characteristics does not meet, the motor characteristics does not meet the load torque characteristics. If you draw the same thing on your own, because I could not draw it, I would have shown it, that would have given you a little more idea. But anyway, you can imagine or you can draw on your papers that if supposing a load characteristic from 0.25 per unit and you draw a straight line, so you will find straight line parallel to x-axis, so you will find a speed change which is actually effective, say, from, say, 0.95 to 0.75, right? 0.75. So then you will see that there is a very less change which is effective. So then for constant torque loads or other type of loads, this kind of say voltage control is not effective, right? So that is why it is written that suitable for applications where torque demand drastically reduces with speeds. That means it is proportional to at least omega m square. Now the second point is there are motor classes, NEMA standards of motor, right? NEMA standards. So you will read in your standards, or probably you can refer some of the literatures. Those, there are different motor NEMA classes, like class A, class B, class C, class D. So they are having different standards. So now we normally concentrate on class B or class D motors, right? Where the NEMA standard specifies the rotor resistance. Now it is written somewhere here. So higher rotor resistance. Now, for class D motors, for same rating, if you have, say, 1 kilowatt motor of class D and same 1 kilowatt motor of class B, let us say. So in both cases, you will find rotor resistance varying. That means rotor resistance is higher for same rating for class D motors compared to class B motors. Now what is the effect? Now, if you remember your say second year courses, or even I don't know third year, it is finished or not. So if rotor resistance is increased in an induction machine, right? So its maximum torque does not change, but the sleep at which it is effective, maximum torque, that actually increases. That means the slope becomes more negative, right? The slope becomes more negative. Torque speed characteristics, this say stable zone slope. So then what will happen? So the maximum torque will appear at lower speeds. That means actually operating sleep will increase. Operating sleep will increase for same torque, isn't it? So then actually whenever the voltage is reduced, so I mean the characteristics become such that you get a wider speed variation. You get a wider speed variation. Now I will show you the case for class B motors. This is the class B motors. So same load characteristics. Now where the rotor resistance is low, that means this characteristics is much stiffer, right? This characteristics is much stiffer, and you find that the change in speed is very less. But for to achieve that lower speed, you need to operate the machine at a very low voltage, and then effectively the sleep becomes unnecessarily large. Okay, the sleep becomes unnecessarily large. So it is at 0.3 class B. So naturally, then the conclusion is that this type of control is suitable for NEMA class D motors, where we have higher rotor resistance, which is effective at higher sleeps normally. Now the problem is that now this is of course one thing, and secondly, you see that whenever you are reducing the voltage to a lower value, so it operates at higher sleeps, isn't it? So whenever it is operating at higher sleep, so what is the effect? So rotor induced voltage is higher, right? So therefore rotor current unnecessarily will increase and will give you a larger copper loss, and then you will see that the efficiency gets decreased, right? And actually this has got this has got an impact when the motor rating is large. Let us say when the motor rating is low, right? Say the fan motors, what we normally use. Actually, I have shown it for 3-phase, but the main application for this is in single-phase induction motors. That is for ceiling fans, or you can say even to some extent the other fans, right? Now there you see that motor rating is of the order of less than 100 watt, say 65 watt, 70 watt, right? So a loss of efficiency by 5% will actually give you a loss of power of around say 70 watt. 5% means 3.5 watt. So it's nothing. Even in your bills, monthly bills, it does not make any impact. But if the same is effective for a 10 kilowatt motor, a loss of efficiency by 5% means actually how much? 5% of 10 kilowatt is 500 watts. So it's appreciable, right? So therefore, actually, this type of control is mainly effective for lower rated machines, and where a loss of efficiency by some few percentage will not affect the overall cost or running cost of the machine. And you can say that the effect is that you can get appreciable speed range, right? Now again, there is some other difficulty for class B motors, disadvantages. Now actually, as I have said, for class B motors, now the operating sleep is much lower compared to class D motors. Operating sleep is much lower compared to class D motors when the voltage is reduced at lower speed ranges, right? So this will give you a further deteriorating effect, like much larger copper loss compared to the class D motors. And then also, the loss of efficiency is much larger. So these class B motors are not suitable for this type of control, for this type of voltage control. Okay. And another point, distorted phase current in the machine and line harmonics by thyristor switching, that I have already said. And poor line power factor, because then if you and the phase angle of the fundamental also reduces, okay, increases rather, you can say, compared to the voltage phase angle at larger switching angles. So 60 degrees, 70 degrees, 80 degrees, 90 degrees, and if you go further and further, so you will find that the fundamental current phase angle is actually retarded, or actually gets lagging from the stator voltage by a larger amount. Okay, so therefore poor line power factor is achieved, and all these things are not actually very much you can say in favor of running this type of control, unless and until you drive a smaller motor. It does not matter. Okay, so that is what it's used for: low power appliance type motors where efficiency is not that important. Efficiency is not that important, right? Maybe it is written here, efficiency is not that important. Right. So is it clear to you? I mean, this voltage control technique?
Yes, sir.
Okay. So now we go for the third type, you can say, variable frequency, that we derived from that the basic principle, like that from this slide again. So here we showed that torque is a function of frequency, keeping other things are constant, right? Torque is a function of frequency. So naturally, we can change the frequency to get a different machine torque, and then that torque will meet the load torque at different operating points, giving rise to a change in operating speed. So therefore, so this becomes the another mode of control, variable frequency control. But first of all, how do you achieve that? Variable frequency? Now, in our earlier control techniques, we could use the normal supply voltage, right? So we used normal supply voltage and applied some crude techniques to vary the voltage, right? It is not a problem. And for the pole changing, it's nothing. We had a connection alterations for the stator windings. But for this one, when you try to shift the frequency from one to another, so naturally it is not so easy. You cannot do it with the general supply. So the first thing comes into mind, the first I think variable frequency technique, variable frequency application technique that comes into mind is what actually? Can you tell any technique which can vary the input frequency or rather output frequency? Have you read power electronics, cycloconverters? Have you read
Yes, sir.
cycloconverters? So the first thing that comes to mind, that we can apply this cycloconverter techniques, right? Where we have of course voltage will vary, but we can control the voltage and make it remaining same. So we can vary the frequency there. And the other technique is actually, which is followed in the most of the cases. So cycloconverters are used for normally big drives, because it uses thyristors, and they are very rugged, and their current handling capabilities, rather you can say power handling capabilities, are much larger compared to any of the devices that we can come across so far. But therefore, I mean, the cycloconverter based drives are for very large drives actually. Otherwise, they have different disadvantages and all, but still for large applications, it is still used. The other technique, which is normally followed from fractional kilowatt machine to larger, I mean, hundreds of kilowatts of rating, to the machines of hundreds and kilowatts of ratings, that is actually, we can convert this AC voltage, which is available at the source, to a DC, and then from that DC voltage, we can generate variable frequency supply through inverters. So inverter based controls. Now it is written here that PWM inverters to control the frequency of the motor. So this is the standard techniques, or I mean that majorly followed technique, you can say, these days. Now frequency can be increased or decreased based on the say requirement, right? But we wanted to vary the synchronous speed. First point marked in red, the speed control above rated or above base speed is actually preferred here, or actually done here, you can say. So why it is so? Now first we saw that one. Okay, we saw that one, that this slide you see. Let's just come to the torque equation and then we'll again tell you. Now the developed torque equation. So from here, I think this slide is visible to you, no? This slide. So the torque equation again I am writing like that. So 3 by, I think it was 3 by s omega s. I think if you remember our earlier derivations. So it is better to write on your paper, so that will help you to understand. Otherwise, what happens? I show the slide, so you take it in your head, and ultimately what will happen after 2-3 days or 1 week or 2 weeks? So you forget everything. So if you write once, so that will give you a better insight, and then you can refer to your book at any time. Although I will try, I'll supply this note, but still, own hand writing is always helpful. Now see, TE actually you can alter that equation. That means that RR by S has been actually split up. That means this is S square XS plus XLS. It will be all XLS plus XLR dot square, and then this equation becomes like this. So 3 RR dash BS square into S by omega S RR dash square plus S square into XC square, you can write the equivalent X, right? The stator and rotor leakage reactance sum. So now you see that then again, if you a little bit have some adjustment, now you can write that Vs by omega S whole square, right? Vs by omega S whole square, and then you multiply here by omega S because it was only omega S in the denominator. So then 3 RR dash into S omega S by this one, right? Now S omega S is nothing but omega SL, the slip frequency, as we say. So now from here we can have few things. That means if the right part remains constant, so torque can be proportional to Vs by omega S square, right? And if rest things are constant, torque is say Vs by omega S is nothing but what? Flux, magnetizing flux, right? If you go back to your survey, I'll show you in the next slide. Okay, this is actually magnetizing flux constant, and then if flux remains constant, now you can write that T is proportional to S omega S. So torque is proportional to the slip speed, right? Torque is proportional to the slip speed. So these two, derivations will be important in our future study. Now you see that how it is like this. So V by omega S, right? So Vm, you write Em. So Em actually, so you see that Im is what? Im is Em by omega E Lm. Em by omega E Lm, right? So Lm Im is your flux linkage, Lm Im, right? So Em by omega E Lm into Lm. So Em by omega M will give you actually the flux linkage. So therefore, actually, as I have written here earlier in the earlier slide, that Vm by omega M or Vs by omega S is actually flux linkage phi m square, phi m. So T becomes proportional to phi m square. So this way. Now we will derive that why at lower frequency, this kind of operation is not permitted, or rather this is prohibited. Why? Now you see that this is the equivalent circuit, approximate equivalent circuit of the machine, right? Just we have neglected the the core loss resistance term here. Core loss resistance term here. So many persons are entering still now. This is EM into, sorry, this is actually core loss is neglected. So now you see that the voltage induced or the stator induced voltage, other air gap voltage you can say, EM, is actually, this is the voltage equation, N d phi dt. So you can just, from there you can derive like this. This is actually 4.44 A phi m into T A. Instead of M, we have written T, number of turns per phase, into kW, the winding factor. So now actually Vs is proportional to EM near rated voltage because the stator leakage impedance drop is negligible. So from which we can write Vs equal to 4.44 F phi m T into K omega, kW, right? So Vs equal to this. So now you see that whenever you try to reduce the frequency, that means for reduction of speed, you have to reduce the frequency as is the basic principle, because we have to reduce the speed of the rotating magnetic field so that the rotor catches the lower speed, right? So then whenever we don't change the voltage but increase the frequency, so flux reduces. But if we do the opposite, that means for lower speed, we reduce the frequency and the flux will try to increase. Now supposing that it was operating at rated voltage and rated flux, and suddenly we have to reduce the speed, right? Then we have to reduce the frequency and the flux will automatically increase if the voltage is remaining constant, right? Voltage remaining same. So then flux increase means what is going to happen? Flux increase means actually that the machine will try to saturate, because normal design of the machine is to operate at near knee point. I mean, not at very unsaturated zone. Otherwise, there will be loss of iron. I mean, unnecessarily the machine size will increase. So to optimize the size of the machine or the iron content in the machine, you will always find that it is operating near knee point, so that an increase in flux will tend to saturate the machine. Now, when the machine is saturated, what is going to which parameter is going to get affected? Can anybody tell? When the machine is going to get saturated, so which parameter is going to get affected?
The flux, the net generated flux.
No, net generated flux is not the parameter. This is the parameter means in the equivalent circuit. Say equivalent circuit parameter, which gets affected, right? XM, LM rather, right? Magnetizing inductance. So magnetizing inductance will decrease. So if you plot magnetizing inductance, so you will find that larger flux, the inductance decreases. So now when XM is decreasing, so what is going to happen? Your voltage remaining same, so the magnetizing current will tend to increase, right? The magnetizing current will tend to increase, will be high. So when magnetizing current is high, then actually magnetizing current plus the rotor current, not plus, it is the actually not algebraic plus, it is actually vector addition, will give you the stator current. So naturally the main effect is that the stator current is increasing. So when the stator current is increasing, actually you see that stator copper loss will increase, right? So when stator copper loss will increase, a larger heating in the machine, heating in the machine will take place, and that will affect the insulation and the machine will get damaged. So that is the reason that we don't prefer means we don't allow. It is not allowed that you operate the frequency at lower value, keeping voltage constant. So that is why actually that this method of frequency control is not applicable to speeds below base speed. That means it is written here in the red point, you see that speed control above rated speed is effective. Okay. So now what happens at above rated speed? Now from here the same derivation, you see that when you go above rated speed, so we can vary the frequency to a higher value. So we don't change the voltage. So normally what will happen? Flux will reduce. So then it is the situation is similar to what we see in DC machine also. Now DC machine above base speed, how do? you control the field control above base speed. That means field current is reduced, right? Here also field is reduced. That means the flux, magnetizing flux is reduced, everything remaining constant. So that is why it is known as the machine is going into field weakening zone, field weakening control, field weakening control. So this actually field is weakened, and the machine, you can say, comfortably goes to a speed above rated speed, and then you can control. Now the developed torque will decrease as because it is inversely proportional to omega s, right? Inversely proportional to omega s. Now one thing I will tell you here from this also, constant torque control and constant power control. So right, constant torque. Now here actually see the flux is reduced, of course, because V by omega s is increasing, Vs is remaining constant. So the flux is reduced. So torque cannot remain constant, right? But omega into T, you see, if you multiply omega into T, that will remain constant. Rest things remaining same almost. So that is why this control is actually the constant power control, right? Constant power control. So stator voltage is held constant at rated value, air gap flux and rotor current decreases, so developed torque decreases, but the power remains constant. Now you see here, so this one. So is this slide visible to you? This TE
Yes, sir.
equal to 3 by omega s Bs square, the same thing I have written, right, into S into RR. So then we have approximated is like this. So since S is very less, so you can SRS you can neglect. So you will find this is RR square plus S square XC square, right? And then for constant load, TE inversely proportional to omega S TE constant. So omega S increases, flux increases, field weakening control. So you have a constant power and torque is inversely proportional to omega S. So this zone is achieved actually. Okay. So could you hear what I said? Because some phone came, unfortunately.
Yes, sir.
Okay. So this is actually the constant power control, and torque reduces with speed. Inversely proportional to speed. Okay. So this one. So omega STE is the same thing. Omega STE is remaining constant. So then actually it is a constant power control, and torque becomes inversely proportional to omega E. So then the next one is actually, so up to this point I think everything is clear.
Yes, sir.
Now this is the plot what we have shown, that actually whenever you see that from say 1 per unit synchronous speed to 3 per unit, the torque speed characteristics that remains like this, right? So I mean, you see that torque is inversely proportional to the speed or something. This is not square actually, this is by mistake it is written omega m T equal to constant. So you will find that the torque, maximum torque you have shown, but for any load you see that the torque characteristics at same slip speed, okay, for same slip speed will be actually parallel to the maximum torque characteristics. Okay, so this is what we achieve with frequency control above rated speed. Now below rated speed it is prohibited. So now we go for the constant volt by hertz control. Now from here I think one slide is missing. Just a minute. Okay.
স্যার এবার আপনি নোটস গুলো একটু তাড়াতাড়ি।
হ্যাঁ, আমি আজকের ক্লাসটা হলে বা নেক্সট ক্লাসটা হলে আমি তোমাদের পাঠাবো। হ্যাঁ, কিছুটা না পারলে
বই ফলো করব।
অর্ধেক অসুবিধা নেই।
হ্যাঁ
অর্ধেক মানে যতটা হচ্ছে ততটা পাঠালেও কোনো অসুবিধা নেই।
না তাহলে কি হবে, আমাকে প্রত্যেকবারই একবার করে পাঠিয়ে যেতে হবে আর কি। এটার জন্য আমি বলছি যে 4-5টা ক্লাস হলে একবারে পাঠাবো। ঠিক আছে, আমি দেখছি যদি আজকের পাঠিয়ে দেওয়া যায়, আজকেরটা পর্যন্ত আমি পাঠিয়ে দেবো, ঠিক আছে।
আচ্ছা
আর
স্যার, বলছিলাম স্যার কি বই ফলো করবো স্যার?
বইটা তোমাদের তো বলেছিলাম প্রথম ক্লাসে, বোধহয় জানি না, মনে নেই। রশিদের বই ফলো করো, MH রশিদ, মোটামুটি কিছুটা আছে। হ্যাঁ, MH রশিদ, এটাতে কিছুটা আছে। আরেকটা বই আছে NK দে বলে আছে, ওনার বইতেও খানিকটা আছে। আরেকটা বই আছে, সেটা হচ্ছে ওই GK দুবে, গোপাল কৃষ্ণ দুবে। এটা তোমাদের অন্য ড্রাইভস এর ক্লাসে মনে হয় বলেছে, ওই হিটিং ফিটিং ইত্যাদি এইগুলোতেও ওটাও আছে, কিছুটা এরকম আছে। বাট আমি একটু অন্যভাবে পড়াচ্ছি, সেই বইয়ের সঙ্গে হয়তো পুরোপুরি মিল পাবে না, খানিকটা বেশি ইয়ে পাবে হচ্ছে রশিদের কাছাকাছি
স্যার নোট
থেকে।
ফলো করলে হবে না?
হ্যাঁ, নোটস তুমি ফলো করতেই পারো, তবে স্ট্যান্ডার্ড কিছু প্রবলেমের জন্য এই বইগুলো একটা দুটো দেখো, ঠিক আছে। তাহলে একটা কাজ করি, ভিভাইএফ কন্ট্রোলটা আরো আধ ঘন্টা 40 মিনিট লাগবে, আমি এটা তাহলে ভিভাইএফ থেকে পরের দিনে ধরবো। তাহলে এই পর্যন্ত আমি তোমাদের তাহলে নোটটা আমি পাঠিয়ে দিচ্ছি। আর ঠিক আছে, আমার যতটা হয়েছে আমি অ্যাডভান্সই না হয় পাঠিয়ে দেবো, ঠিক আছে, আমি দেখে নিচ্ছি ঠিক করে। হ্যাঁ, আর তোমরা আজকের অ্যাটেন্ডেন্সটা আমাকে একটু মেল করে দিও তাহলে। হ্যাঁ, আর নেক্সট হচ্ছে,
ঠিক আছে স্যার, আজকে অ্যাটেন্ডেন্সটা স্যার তাহলে দাঁড়িয়ে জানাচ্ছি।
হ্যাঁ, আর নেক্সট হচ্ছে তাহলে আমি যতটা হয়েছে অতটা পাঠিয়ে দেবো, দাঁড়াও। আর যতটা এক্সট্রা আছে দেওয়া আছে, যতটা আমি করে দেবো। নেক্সট ডে তাহলে ভিভাইএফ থেকে শুরু করবো। হ্যাঁ, নেক্সট ডে হলেই হয়তো ইন্ডাকশন মেশিনটা আমার হয়ে যাবে। হ্যাঁ, ভিভাইএফ কন্ট্রোল, ইমপ্লিকেশন ইত্যাদি। তারপরে হয়তো ডিসি মোটর আর সিঙ্ক্রোনাস মোটর। মোটামুটি এই মোডে পড়িয়ে না একটু তাড়াতাড়ি হয়ে যাচ্ছে আর কি, কারণ বোর্ডে হলে আমাকে আঁকতে হতো ইত্যাদি, এগুলো টাইম লাগতো। তাতে তোমাদের সুবিধা হতো, তোমরা অ্যাসিমিলেট করতে বেশি সময় পেতে, কিন্তু এখানে তো অ্যাসিমিলেশনের সময় পাচ্ছ না। যাই হোক, আই উইল ট্রাই। হ্যাঁ, তোমরা একটু পড়ে টড়ে দেখো, আমি পাঠিয়ে দেবো যতটা আছে। আমি এখান থেকে একটুখানি, এটা একটা অন্য একটা লেকচার নোটের পার্ট, সেটাকে আমি খানিকটা ক্র্যাম্প করে যেটা যেটা তোমাদের লাগবে করে আমি তোমাকে পাঠিয়ে দেবো, ঠিক আছে। কালের মধ্যে আমি আশা করছি পাঠিয়ে দেবো, কাল পরশু মধ্যে, ঠিক আছে। ওকে। এই তো কে অ্যাডমিট হচ্ছে এখন, দ্য ক্লাস ইজ এন্ডেড। রঞ্জন, ক্লাস ইজ এন্ডেড। হ্যাঁ,
ঠিক আছে স্যার, আমরা ছেড়ে দেবো।
হ্যাঁ, আমি বেরিয়ে যাচ্ছি, ওকে।
Okay, thank you, sir.